Right. It gives me great pleasure to introduce to you Professor Lydia-Joubert. She's a South African. She started her career here in South Africa as a botany. Her studies were in botany, plant sciences. Moved to the US, learned and focused on electron microscopy, and then in the mid 2016. 2016, she came back, or 2017. Why do I think it's 2017?
2017.
Yeah, 2017, she offered her services to our microscopy unit and said she wants to come and invest back into South Africa. Unfortunately, the Americans kind of lured her back to Stanford University, but she's still now in a mentorship role in Stellenbosch. She has some students. She's an extraordinary professor for the university. So we thought she has a very long career. She started in plant biology.
Oh, yeah.
She's a microbiology professor today, and she works at a medical facility. So she covers quite the range. So we thought to ask her to tell us about training and her career path and kind of motivate the young ones here on what does a good career path look like, and what was the main points in your life that brought you to where you are now. So thank you very much.
Thanks so much, Lisa, and thanks for the invitation, Yara, everybody. And yeah, we finally came to the closing of a very exciting and very dense week. I hope you still have energy to focus, but this will not be too intense. I hope to make it a little more fun than the previous very intense presentations. And I was also wondering this morning, you know, we're coming at the end of this. There were so many exciting and inspiring talks and presentations, very thought-provoking arguments. And what can I contribute still to, you know, inform people or inspire people? But I'll stay to the regional plan, exchange of experience, and take you a little bit through my unconventional career path and where it started, how I landed here, and then especially in my experience in microscopy working between different continents, the African and American continent. It took some time to do that. But first I want to, let's see if the technology works. Yeah. I want to bring us back to bioimaging, and that I know we are all informed about bioimaging. Why do we do it? But I often get that question when I talk to friends, family, relatives, say, why bioimaging? Why are people even interested in it? But it has been recognized by not only scientists, but also governments, policymakers, funding agencies, the importance of bioimaging to address the grand challenges in biology. And these vary from cell community interactions right up to drug development. And it spans across several complexities and also then several spatial resolutions to which we can assign different imaging modalities. Of course, this just focuses on microscopy. But you can see here that from X-ray microscopy, which is about in the micrometer range, right up to crystallography, and Cryo-EM, which is the field I'm currently in, where we go to the angstrom range, currently about 1.2 angstrom structures that we can resolve. We need different technologies and modalities to address different challenges. And very often that is our biggest challenge, is to know, the scientist is to know what to choose, where to find it, and how to address it. Now I'm going to stay back and take you to my life experiences and how to get there. So small beginnings. My life really consisted and still consists of chasing opportunities, hunting down opportunities, and then jumping for the occasion. So South Africa, 1960s, that was my first experience at a school. In the desert area on the west coast of South Africa. My parents are both in the teaching careers, and this is where I had my first awareness of a school. I was still preschool. There was no other child my age in a 50-kilometer radius, so I would just join in and shadow twinning with the other kids in school. And this was our closest neighbor, a Caucasian, as we say in America, Caucasian woman who was doing the school's washing by hand. There was no electricity in the area. And she lived in this reed house. That is now a ghost town. It doesn't exist anymore. From there, my dad decided to establish a school on the edges of the Nizam forest. Those of you familiar with Deline Mathieu's books, my fellow scholars, pupils, learners, as you say here, were woodcutters, children, foresters, and then also immigrants to the area. So really a multicultural, multi-language area also, Afrikaans, English. I know our teacher spoke only French. So we were only 3 in the class. That is the entire school from 1st grade to 7th grade. There we are. And then from there, moving on to the beautiful town of George. And that's the first time that I became aware of opportunities. I was probably overwhelmed by all the opportunities. And often in education, you hear the saying, you can take a horse to the water, but you cannot make him drink, but you can make him thirsty. And I think I was more than thirsty when I got there. So I tried everything. I took part in everything. And I also became aware you have to take up an opportunity. To just look at it and be aware of it doesn't take you anywhere or bring you anywhere. You have to grasp the opportunity, and you may have to work for it, and sometimes work very hard. So after that, just briefly, BSc here in Stellenbosch, Mathematics and Botany. Then I got another opportunity to do an internship at the Weizmann Institute in Israel in the 1980s. And electron microscopy became part of my life. Since an honor student, then through my master's, electron microscopy, TEM and SEM, and also some fluorescence microscopy, which was still, there was no confocal in those days, no molecular biology really. But the journey continued, and then I got another opportunity to continue with my PhD, or the major part of my PhD at Indiana University, in Bloomington, Indiana, in the United States. Then finally got my PhD and settled in Stellenbosch. And of course, as microscopists, we are not perplexed by small beginnings. Look where we started, and look where we are now. And even more, this is what our cryo-electron microscopes look like now, but only on the outside. This is how we move then in. This is one of the 4 Cryos instruments we installed in the past 2 years in our Cryo-EM Center in the one building. The other building, we have 4 more of those. So it's a really exciting time for microscopy, and not only for cryo-TEM, because all the modalities are really needed to provide the answers that we want to provide in research. And then, yeah, just to load a sample, this is what the interior of the microscope looks like. And most of our training is focused on helping people to use these cutting-edge instrumentation. Then another opportunity. I got the opportunity in 2005 to join the Beckman Center Imaging Corps at Stanford University. That was a very, very interesting time to join a medical institution and especially become involved in scanning electron microscopy, because that was the time when array tomography was developed. I worked closely with Stephen Smith and his team. His electron microscope was in my facility. And what we have as core facility people have the privilege of doing, we can tie on to technologies that are being developed in a certain field. So array tomography was developed for neurosciences. They looked only at brain samples, but at the core facility, we get multiple other samples. So we could apply that technology to lungs and nasal tissue and organoids and stem cells and anything that would be fitting for array tomography, we would try it on. This was the paper that we published eventually here. This was varicella zoster infection of mammalian cells. In addition then to array tomography, I was introduced to the entire field of volume EM, serial block phase SEM, which eventually gave rise to the Aprio volume scope in Tygerberg, and then also environmental SEM, which is what it was at that stage very important to develop scaffolds for stem cell growth. And on top of that, X-ray fluorescence. We have the beamlines, we have the synchrotrons in the United States, easily accessible. And here I was doing micronutrient requirements of Helicobacter pylori, the stomach ulcer, stomach cancer bacterium, and synchronizing then or correlating SEM with your X-ray fluorescence signal. So all these opportunities were there. And most of them you had to work for very hard. For instance, the synchrotron, it's not easy to get access there. Even when you get access, you have a lot of trainings to do, online trainings. I was not an American citizen at that time. They screen you really before you. Now I'm an American citizen also, and South African, but they screen you for access. You cannot easily, as a foreigner, get access to all the American facilities. South Africans mostly don't have a problem though, I can assure you that. And then, yeah, the argon was the synchrotron where I did those type of analysis. And with so much input, you expect output, and that the importance of publishing what you work on cannot be stressed more. And the privilege we have at core facilities, and I was then at a core facility, a paid-for service, is you can publish in a variety of fields, not only methods and methodology. In this case, we were working on Cryo-EM with battery interfaces. This was involving Clarity. Clarity is you're probably familiar with Clarity, developed by Carl Dijsselroth. This is a paper that I had the privilege to work together with them. Then this was the first FIBSEM that we did on cells that were growing on quartz pillars. And at that stage, there was no other modality that you could really use outside of focused ion beam SEM to mill through your hard and soft materials. But the life sciences was very poorly presented in the material sciences side, still probably is. So the sample preparation was something that the people working on their scaffolds, the quartz crystals and quartz pillars, didn't have any information about. So then the interfacing of people from different microscopists, from different backgrounds become very important. Another biology paper, nanoparticle probes being developed, cadherin fingers, endothelial cells, again, nanoparticles with the same group, and then most recent Cryo-ET paper that we produced from our own facility at SLAC. So what I want to point out here is you can see on all these papers, there's always, the least here is 8 co-authors or authors on the paper, and it's mostly up to 20 authors. Science is no longer done in isolation. You cannot publish if you're only just you by yourself. And then at a facility, it's important to find collaborators or make yourself visible that people want to collaborate with you. And then at the same time, we are in an ideal position to also connect people that we know work in similar fields. So they may not be aware of themselves, of each other, but you can point out to them, these guys are working on H. pylori and you come from that institution, they're working on the same thing. Maybe you should meet and you introduce them to each other. And very often you stay involved in that type of collaboration. So that's how you build these type of connections and networks. Then another opportunity after all these exciting things, as Lisa mentioned, and it actually started with an endurance hike I did here in the Karoo, 260-kilometer hike, and they were launching the correlative imaging platform, and I spoke there, I had a talk presentation there, and then they started, working on me to come back and gave me an excellent job offer, which I couldn't resist, and I said, okay, this is my time, this is my solo EM safari, I'm going to do it. So I left my family behind in the United States, husband and 3 sons, and I came here to 2 challenges, 2 missions. The one was to develop biological EM on the main campus, because as you saw today, those of you who were in the EM facility, they have excellent instrumentation, but mainly focused on geology, analytical EM with very little awareness of what needs to be done for biological EM processing. And that, as you know, is a completely different discipline almost. You have to understand the chemistry and the physics of what you are doing to the samples before you put them into the microscope. So then developing from a very basic, we didn't have water in the lab, I remember. So you saw the little wet lab we developed there, all the basic processing equipment. That went very well on a shoestring budget, really. But everybody was very enthusiastic. Some of the main challenges was to drill through a 50-centimeter, 100-year-old wall to get cables pulled through. And then also to get everything prepared. Now, I'll come to that later for the load shedding that was already looming on the horizon at that stage. And at the same time, there was a very exciting opportunity to take part in another round of NEP grants, as we call them. So for people not South Africans, the NEP is a national equipment program from the government, from the National Research Foundation. And it can be up to a maximum of 15 million rand, which with the current exchange rate doesn't sound too much, but at that stage, it was about $1 million. And you can buy quite a bit of microscopy tools. You could then in 2017-18 for $1 million. So, and the university needs to contribute 1/3 of the amount, and then the NRF would contribute 2/3. Competition is really severe, and something that I later realized is very different in South Africa from what I had in America on grant rounds, it's very important to show that you have international collaboration when you apply for a grant in South Africa. In addition to teaching, you need to have, be able to supervise students. You have a record of supervising students. You need international collaboration. So I think that contributed to our success. I immediately contacted all my Stanford collaborators and said, help out now. The only thing we need you to do is to say that you're interested to support us here, and they did, and give your background and your association to me. And they've really been, some of them even sent me samples here, shipped samples, so we can continue to process and image them here and have a project started with Stellenbosch. So we were successful with various NEP grants in that year. It actually came out in the news. We are putting, let me read there. The NEP grants put Stellenbosch University on the forefront of molecular imaging in Africa. Of course, the grant and the instrument arrived before we had the room. The beautiful building you were in didn't exist yet, and COVID didn't happen yet, so it wasn't delayed. So eventually we found a room with one hospital bed on the 6th floor of the clinical building. And in record time, that was revamped. We got all the facilities done. And the microscope was delivered by Thermo Fisher. We got a person from the Netherlands to come and train us. And then eventually, you were there yesterday, this instrument moved into the beautiful new Biomedical Research Institute. In the meantime, COVID happened. I was called back to America, but we had a great neuroscientist who was a student also of Ben Lewis, who was taking over the daily operations of the microscope and developing the facility further. And now you have Janika, who was thrown in at the deep end, but she's swimming pretty well. And I'm very proud of what she's already doing at the facility. So there and back again. So I mentioned the calling that I got again from the job offer from Wachu's team at the Cryo-EM Center at Stanford. So what happened in America then was Cryo-EM was seen as an essential tool to be developed. And the NIH put in a huge effort, a huge grant effort to develop Cryo-EM and then later on Cryo-ET also in 3 different centers in the country on the Cryo-EM side and 4 on the Cryo-ET side, realizing not every institution can afford to have all these facilities. It's simply too expensive. But if you can establish these research centers in different locations and give access to the entire research community in America, and now we also have outreach to abroad. We have users from the East and from various other countries, not from Africa yet, but hopefully soon. You can actually then inspire and encourage research and support research without having to fund individual institutions. So here we are, just want to point out a couple of things here. This is our grounds. We're on the grounds of the national, on one of the light sources on SLAC, which is Stanford Linear Accelerator Center, one of the microscopes. That is my SEM lab, so that is part of the cryo-FIB SEMS. We have 2 of the aquiloses, which is used for cryo-ET sample preparation, and we just got funding for a Hydra plasma FIB also that should go in between the 2. Here we're moving instrumentation between buildings. There's always some space that needs to be either revamped for another instrument. And this is a development we're currently doing with Delmic, which is a company in the Netherlands, to develop a tri-incident stage and higher resolution integrated fluorescence microscopy. So we now have fluorescence microscopes that are built into our electron microscopes, so you can do guided milling operation and target your region of interest very precisely. Okay, so back to a little bit, how do we know what to ask for? How do we know what we need? And this takes me back again to when I was about 4 years old, turning 5, coming from that desert region, going into a grand restaurant, and my parents told me, you know, choose what you want for lunch. And I asked for a tomato sandwich. And that became like a family joke. You know, I could ask anything and I asked for a tomato sandwich. But what do you know to ask for if you don't know what's available? I couldn't read. I didn't know what to ask for people. And that actually became to me like a metaphor. How do you know what to use in your science, what to ask for if you don't know what is on the menu? Not only in the imaging modalities, but then also in what technology is available, how to get access to it, what is the pricing, where do you get funding from, who do you talk to, how do you get collaboration, how do you build a community? These are all questions I think people who enter into a scientific career have, but we who have been there for a long time don't necessarily know it or realize it. And then also as new technologies become available, if you're not really networking in the field, you may not know what may be applicable to your science or your scientific research question. So I think that's become very important. That is why we are here. That's why the group is here. That's why Bioimaging Africa, Global Bioimaging, all these incentives have started. Briefly, I'm not going to focus too much on the technologies because I know everybody wants to get home. We have 2 centers currently at SLAC. Our S2C2 is our single particle data collection center, and then SCSC is the Stanford/SLAC Cryo-ET Specimen Preparation Center. We specifically call it specimen preparation because the data collection in the model that the NIH proposed, the data collection is done at a single hub and not at the individual spokes of the hub. They may revisit that model though. Single particle data collection, those of you attended Jeremy's talk will know what it's about. It's really about imaging particles, which are macromolecules, proteins, viruses, small vesicles, and these samples all need to be vitrified, frozen. You want to embed them in a thin layer of non-crystalline ice. And then eventually you want to get a structure like that. You want to solve a structure that is ATPase at, I think, 3.4 angstrom, or we're all familiar with coronavirus spike. That is not SARS-CoV-2. That is another coronavirus. We don't have a BSL-3 environment, but we focused on other coronaviruses and actually found very interesting information that may be translated into the SARS-CoV-2, say, drug discovery also. On the Cryo-ET side, you use similar and different instrumentation. So here you will have, say, a bacterium or a cell or cell clusters growing on grids or transfer to grids. And now you focus your electron beam on the edge of the cell so that you can collect a tilt series from -60 to 60 degrees with a tilt axis, according to the tilt axis of the microscope. And then that tilt series is reconstructed into a tomogram. And from that, you then do segmentation, annotation, and 3D reconstruction. That works very well if your cell is thin enough or the cell edge is thin enough that the beam can go through it. But as soon as you have anything larger than a yeast cell, I mean, a yeast cell is too thick, you have to start milling away the majority of your cellular material to just have a 200 nanometer, what we call a lamella, that then goes into the TEM. So you start with your focused ion beam SEM, mill your lamella, move your TEM grid into the Cryos or the Glacius 300 to 200 kV microscope, and then collect your tilt series on that lamella. So it's a multi-step procedure, very tedious. It often takes people 2 years of sample preparation and collecting data before they've solved any structure. But here we now take the proteins that we solve the structures with single particle analysis and put that into the context of the cell, of the cellular environment. So you don't have these isolated proteins, you have the cells in situ, and you can also, and you still have that in the native hydrated environment. So the communal factor between these 2 technologies is that every sample needs to be vitrified. Minus 180 degrees Celsius, liquid nitrogen, liquid ethane, and they need to be kept vitrified through the entire process right up through data collection. And the beauty about these centers, they are run like synchrotrons. So especially at SLAC, you apply the same way that you apply for beam time at the synchrotron. You have a project proposal, then if that is approved by a review committee, you can have access to the facilities, you get training access, and we now have a screening program, a training program, and also remote data collection for people who just ship their samples there. Just briefly. And then also our mission, I think every imaging center needs a mission. We focus on access, support, and training. And under that, we have access to instrumentation for sample preparation, data collection, and also access to experienced staff scientists, support for screening and optimization, data collection, and data processing, and then training in sample preparation, microscope operation, And also we have project tailored and comprehensive training. So people may come with just one specific project they want to have an answer for, or other may come with, they want to know more about cryo-EM. They don't yet have a specific sample, but they want to start their own career and want to know more about cryo-EM, so they can come for comprehensive training. We also have people coming there for sabbatical or 2 or 3 months. They get free access to the instrumentation. We do not currently have grants to support travel and lodging, but in America, there's recognized now the disparities that we also have in communities there. So if people come from the so-called idea states, then they can also get support for lodging and for flights. And idea states is, it's an acronym standing for Institutional Development Award. And that is because the NIH also realized that there are many institutions who never get any grants from them. So it's most of the West Coast and the East Coast. You go Boston, New York down, and then you go Seattle, San Francisco, San Diego. These institutions get most of the grants. And then some of the other institutions are so-called teaching universities. There's hardly any research done. And some of what America, they refer to the flyover states. So there's a real purpose now also to reach out to these universities and involve them also then in this access, support, and training, and get them involved as collaborators in this type of research. On to democratization. There, it's not only about saving costs, I later realized, but also about providing access, democratizing access to scientific equipment. The most popular person probably here is Manu Prakash with his frugal science and the fold scope development. He also started a whole community in microscopy. His mission is to have every child on Earth be able to possess a fold scope, a microscope, a $1 origami microscope, the way that every child should be able to have a pencil to write with. And he created this whole global community, and you can follow the blog on Microcosmos, and people, you can take pictures with your smartphone and then upload that onto the blog of Microcosmos. And he's also doing great work here in South Africa. I think he's connected to UCT. And when I was here, I ran some workshops for him. We have desktop EMs. You don't get the same resolution, but you can do electron microscopy. That's also more frugal. Low voltage microscopes. Thermo Fisher now came up with a Tundra, which is a 100 kV microscope for $1 million, which is much less than these Cryoses, which go for $7 million. Ease of operation. They're integrated workflows that is controlled by an interface with the instrument. I was quite surprised when I was 2 weeks ago working with a vendor who makes this almost $1 million freezing instrument. And he said, well, that is to democratize science. And I couldn't understand how you can sell a freezing apparatus for $1 million and say you democratize science. But the workflow makes it very easy for anybody to be able to run it. So if you have some of these instrumentation at national labs and these type of national facilities, and people can get access to it through a project proposal, you really democratize science because you make these instrumentation available for anybody who has a suitable research question. Then access and national centers and X-ray beam lines, they are free of charge. Core facilities, it's a paid for service. But what I found in my area is because people don't always get enough time on the cryo-EMs, we really work hand in hand with the core facilities to also recommend people to continue with their research. If they want more time, go to, say, UCSF or Stanford or UC Berkeley or one of the other universities in the neighborhood. Of course, if it's not within your budget, it can be, SCM is like $500 a day, and a cryo session may be $1,600 for an overnight data collection. So that may be beyond the budget of even very prominent labs in the area. That is the Chameleon, which is the one of our freezing equipment that we recently got. Very, very automated workflow. It's actually, once you've got familiar with these type of instruments, you want to make it a workhorse, although it's not applicable to all types of samples. The beauty of these more cutting edge instrumentation, you very often use only picoliters of sample to prepare a grid. And then on this slide, this was a recent science paper review. $7 million for a large instrument, 300 kV microscope, less than $1 million for the 100 kV Tundra instrument. But in addition to that, and that's in the small print there, the room preparation may be hundreds of thousands of dollars. And that is something that people also don't always understand or expect, that as soon as you go to the more cutting edge instrumentation, your building requirements and room requirements and getting the environment prepared for the room or for the instrument may also be a very expensive thing to budget for. On optimization side, something we really spend a lot of time in, and I think this applies to all modalities, not only to cryo-EM, is workflow development. The more advanced the instrument is, the harder it is to operate it, the more detailed you need to be in showing or teaching your users how to use the instrument and how to prepare the sample to be ready for that instrument. So we do that in pictures, we do that in text, having diagrams to show people exactly what the path is they should follow from A to Z. And then with integrated fluorescence, the path becomes even more complicated. As you can see here, you can do your freezing, then fluorescence, or you can take your sample right through to the SEM, do your fluorescence inside the SEM, and then mill accordingly. I work very closely with my users to prepare these type of workflows and SOPs. So as you know, when you get an instrument, when you purchase an instrument, there's mostly some training that goes with it. It's included in the quote. But after that training, only you as a manager or a director of your core facility and your staff know how to use the instrument, and it's not necessarily or really suitable for your specific samples that you want your users to run. And every user may have different requirements based on their samples. So in addition then to our workflows, we also then go to preparing SOPs and working closely with the users and allowing them also to adjust and edit and change the SOPs according to their needs and workflows. And then this type of workflow to show what all instrumentation is that you may have available, and depending then on the sample to start with, the thickness of the sample, which route you should go through plunge freezing or high pressure freezing, and through the different equipment that is available. It looks more complex than it is, but that is what we have on site, and that is what we discuss with our users before they start and embark on a new project. Training approaches. So maybe we can also call it optimization, not necessarily standardization. In cryo-EM, because of the strong focus in imaging currently on cryo-EM, the NIH funds also then funded a development of a cryo-EM 101. So there's a link embedded in the slide. So if you get the slides, you can go there. There's a cryo-EM and cryo-ET 101. That's a full curriculum that's being developed for cryo-EM. And before that, even we had Grant Jensen. It's on YouTube videos. I think there's about 40 hours of YouTube videos to watch. And he's a very, very prolific speaker, and explains very clearly what cryo-EM and cryo-ET is about. One problem we had on site, though, is because we're on a DOE site, the wear of PPE is very important. 1 minute. Okay. So we had to prepare our own videos where people wear the proper PPE, because in Grant Jensen's videos, people don't wear PPE, but we can still make people aware of it. Merit badge program, that is to train people at one facility, they pass a test, they get a merit badge, and then they can use the other facilities' instrumentation without any additional training. And then we also involve virtual reality for our training. Workshops, I just want to show you workshops look similar around the globe. I have some dates there in Stellenbosch, some at Stanford, excited people. Yeah, there's a lot of energy in having workshops. Infrastructure, that is also a surprise and came as a surprise for us also. Going back here, engineers, working closely with the engineers, talking to them while they're installing the instrumentation to learn what it's about. We also have cryo lift out, which means you have micromanipulator tools inside your SEM that you can mill out parts and pick it up. Too much detail, I think. At Stellenbosch first, the last one, disaster management. That is something that one doesn't always think about, but all around the world, we have disasters that we have to be prepared for. In Stellenbosch, it was the looming load shedding. We rewired the entire lab. We got UPSs connected to generators and we learned how to keep the microscopes running despite the power going off. Also learned how to put things down safely and start them up safely, which is something you don't necessarily think that you need to learn how to do with an instrument. But then at Stanford, 2023 happened. We had a safety stand down enforced by DOE because an electrician was electrocuted while doing repairs on a high voltage line. He was alive, but the Department of Energy put us on a safety stand down and no high voltage work was allowed. And then extensive paperwork and authorization, pre-job briefings to go through to go online again. But even though we could continue our work, no repairs were possible on buildings. So we lost our HVAC, we lost our nitrogen in the building, and we were not allowed to have any repairs done, even though we could do repairs, but that was not allowed because these were all behind a high voltage breaker. You can see 91 degree Fahrenheit inside the room. The instruments started failing because the temperature is too high. There's no dehumidifier in the room. And then the winter storms happened. So we had these power outages that ran for 3 days. And yeah, we kept going in a way. We learned to, I told people it's because I learned how to redesign infrastructure while in South Africa, that I could actually redesign the infrastructure to keep the instrumentation going. Mind the gap, we've already talked about mind the gap earlier. Mind the gap not only between continents or countries, in every single country, you have gaps that exist in expectations and what's really happening, funding that's available versus what you need. Data storage and computation I haven't even touched on, but there are gaps everywhere. It's not uniquely in South Africa or between continents. So we have major gaps also in the United States. Then just for the beauty of it, let's see if it's going to start now. The importance of not only seeing or visualizing at higher resolution, but visualizing in context. And this slide, I think I want to remind everybody that we're really dealing with the beauty of life. Every day that we work, we visualize samples, and we see life that in the way that no other person who doesn't have access to this type of instrumentation can do. So this then is a very talented computational person on site, Muyuan Shen, and he used some of my tomography data and then overlaid single particle data. And this is a fly through the chloroplast of Chlamydomonas. And you can actually see here your ATP synthase, and then you see your PS1 supercomplexes, PS2 supercomplexes, all the individual protein complexes can be visualized here. But that's another job opportunity because we still need narration, we still need music. This is just beauty. And we need to see this in context and understand what we're looking at. And then just a fun slide. There is no purpose in having sharp images if you have fuzzy ideas. So the mind, the human mind, and just formulating your research question, understanding what you're looking at, that is sometimes more important than having the most cutting edge instrumentation. And yeah, thanks to everybody, my team and the team here. Thank you.